Yes. Okay, good. So, welcome everybody and welcome people online. We are very pleased to have a student from engineering today, Merve Karabulut, who's already presented here last year, and she's going to update us with her research on side channel analysis on the new post-quantum standards. So she's going to give a talk on efficiency P attack on hardware implementation of ML-DSA in post-quantum root of trust. So thank you very much for coming here and present.
Thank you for having me. So I'm working with Dr. Reza Zardarashk, and this is my second year for my PhD. And we are focusing on post-quantum cryptography and their side channel assessment. And we did a side channel attack on ML-DSA. So I will be talking about it. So for my presentation, first, I want to talk about our research motivation. I will briefly talk about our context. Then I will go over the background of PQC, side channel, and ML-DSA itself. Then I will show our proposed attack. Then I will share our experimental setup and our result too. Then I want to talk about countermeasure, which we weren't able to talk, and what can we do in the future work. And I will also give conclusion. So we perform the first side channel attack, a specific implementation of ML-DSA in root of trust system using 10K power measurements. So the world is moving toward post-quantum cryptography because right now we have a new threat called quantum computers. And that's why NIST initiated a PQC standardization process, and ML-DSA was selected for digital signatures. And their side channel assessment becoming essential for us because, yes, they are quantum resistant, they are powerful, but their physical implementation is still leaking information. So that's why our main question is that, can an attacker extract the secret key using side channel of this quantum PQC implementation? So that's why I will roll it back and I will talk about the general cryptography. I'm sure you already heard this verse many times, but I want to talk about the digital system way. So the means is secret writing. We want to make sure that our data is secure and private. So it is not going to be available from like unintended parties. That's why we have cryptographic scheme, and we want them to be consist of hard math problem. So it is not going to be easily solved by attacker. And also we want them to have their standardized and efficient implementation so that it can deploy it in real world application. But as I said, there's a great mathematician, Peter Shor, and his algorithm proved that the current classical algorithms such as RSA or ECC cannot stand against quantum computing because their math problems, the gives the strength to them, can be solved by these quantum computers, which their problem was mostly discrete logarithmic or factoring large problems, factoring large integers. So that's why NIST, I believe in 2016, started the PQC standardization process to ensure that we have cryptographic algorithms that secure in the quantum era too. So they focus for digital signature and as well as key encapsulation, and they selected 3 algorithms for digital signature. The first one, ML-DSA, model lattice-based digital signature standard. So the other one, Falcon and Sphinx. So the reason that ML-DSA was getting attraction, especially from industry, is that it is efficient. The key sizes is it is okay for real-world application deployment. So it is started to being used in industry and major tech companies. But before that, I want to talk about the general overview for ML-DSA. What is the problem over here? And what do we have? What structure do we have? So the security of ML-DSA relies on model learning with error and model short integer solution. which I'm not that much confident about this problem, but I can talk about their side channel part. So it is operating over polynomial ring, and we have a modulo value Q. And so this scheme includes 3 parts: key generation, signature generation, and signature verification. But I already said that for side channel, we are trying to extract the secret key. So that's why I will focus on the part that including secret key, which is key generation and signature generation. So this is general overview of ML-DSA. The first part showing the key generation, the second part signature generation, and the other part verification. So I highlighted the secret key components with red color, and the black color is public information. So anyone can calculate this public values. So let's go over for key generation. First, we have a seed, and using this seed, we are generating S1, S2, and public information A. And we have a public vector T. And idea of model learning with error is that let's remove this S2 from this equation. So we know T, we know A, so it is easy to find S1. But if we add S2, it's going to be additional error that attacker is not going to find the S1 easily. And our public key consists of row and P1. So T is public, but we are getting high bit of T, which is T1. It is public, but the low part of the T, it is private. So it is called T0. And private key is row, K, TR, S1, S2, and T0. But as I said, like row, K, and TR can be calculated giving these values. So for signature generation, we have the method called Fiat-Shamir with abort. So we are calculating a signature Z, and if it is too big, we are rejecting and trying to find a valid signature. So as you see, our private key components, T0, S2, and S1 being used, the point was multiplication with C. Okay, we have the idea of ML-DSA and how it's working, but I want to talk about how they're being used in hardware system, digital system. So we are using this digital signature algorithm in our trusted platform models or hardware security models. So trusted platform models, TPM, basically a chip in our computer, which is storing all the private key, all the information that requires confidentiality. And they are being digital signature authenticate transaction, and they are doing these messages and identity. And we also using digital signature algorithm in IoT device authentication, because we want to make sure that this little device has will be authenticated user that will connect it to the network. So they have a unique key pair stored in their secure hardware. And basically it signs the message to authenticate itself to the server. And also we are using secure communication, TLS, and SSL. These certificates use digital signature to establish secure communication. And also VPN, we are using this digital signature algorithm. But we attack Calyptra. So Calyptra was using ML-DSA. It is an open source root of trust module developed by major technology companies, Microsoft, AMD, Google. And the idea, Calyptra, is that they are going to use this chip in their data center security when they want to provide firmware integrity and cryptographic operation. So, but what is this Calyptra? So idea is that we have this chip, but we want to make sure that the only authenticated firmware is executed in this chip. So it basically providing secure boot and firmware integrity. And it has many cryptographic operation with ML-DSA, and it was implementing this secure key management and cryptographic operation. And it was when they were doing their announcement, they said that it is a post-quantum cryptography ready, and it was open source. So it was developed in collaboration with industry partners, and it was available from the beginning. So that's why, yeah.
Just what does root of trust mean?
Sure. So root of trust is a basically hardware component that is providing all the secure operation. So let's say that when we running our computer, we want to make sure that this bootloading is being securely. So no one except us is not going to run this computer. So that's why I said computer, but let's think a very basic idea. So there is a chip produced in Thailand, okay? The chip was made by Microsoft and they are selling us. So they are giving us the private key for this root of trust system. And they are embedding this public key to the chip. So since we have a secret key, the root of trust ensuring that we are the authenticated user that is running this chip. So we are signing this private key, we are signing our firmware with the secret key, and the public key can verify us, whether we are authenticated user or not, so that there's no malicious software is going on this chip. So root of trust is basically responsible for this all secure boots and secure firmware integrity. Of course. It was a really good question because it is kind of like confusing part most of the time. And it is hard to connect with the cryptography. So this is their high-level block diagram. So they have like a CPU, is V core. It is basically managing all this thing. It is a CPU. And we have a ROM. ROM basically storing this firmware. And we have cryptographic subsystem, which is all the cryptographic operations such as SHA, AES, ECDS. So it was also collaborating with ECC when it comes to this certificate generation, and they have like a key vault. So ML-DSA, as we said, the firm image is signed using ML-DSA by trusted authority before deployment. And when the system boot, Calyptra verifies the firmware ML-DSA signature using preloaded public key. And if the signature is valid, the firmware is executed. Otherwise, the device refuses to boot to prevent unauthorized modification. And this is how they use ML-DSA in their implementation. But okay, it is great. They are resistant to quantum computers, but we want to make sure that their physical implementation is also secure, because side channel is a real threat for us. But what is side channel? Okay, I'm always telling side channel, but I didn't have a chance to talk about the background of side channel. So Paul Kosher, he was actually a vet, but he was into cryptography, and he did the first side channel attack in a conference called Crypto 99 with his friend Joshua Jaffe and Benjamin Jun. So the idea is that DES back in the time was being in smart cards. So idea is that let's measure the power consumption of this device when the DES is going on. And by analyzing the power, they were able to extract the secret key of DES. Then his study expanded in a way that we are not just using power, we can use EM emission of this device. And even execution time, even the sound of this device, like acoustic part. Idea is that an attacker has the ability to send plain texts and they get the ciphertext. And during this cryptographic operation happening, attacker can able to observe this environment to extract secret key. And this is the general idea of side channel, but how we are going to know that this implementation is leaking information side channel vulnerable? So there's a test, it is called test vector leakage assessment. It is called TVLA. It is a statistical method used to detect side channel leakage in cryptographic implementation. Idea is that we are sending two different data sets to this device. So when I was learning, the idea is that flip a coin. If it is a tail, send fixed input. So it means that whenever sending this, whenever we are collecting power traces, it is going to be same data. Let's say that we are always sending 0. But if it's a head, we are using random inputs. So different data for all traces. And the device process these inputs while we record the power consumption. And then we have like very basic formula that we are doing, calculating this t value, getting their mean and also their standard deviation. And this TVLA giving a plot. And if this t-score exceeds 4.5, it means that they have a side channel vulnerability. As you see, their ML-DSA implementation has a leakage. And we got this leakage even 1,000 traces. So TVLA methodology says that if you are getting a leakage in 1,000 traces, it means that you can attack using 1,000 traces. But since it was a hardware implementation, it has a noise that is kind of hard to get rid of it. But eventually we have idea that, okay, at least we can attack. Okay, we kind of know how these things work, but we don't know how this secret key being used and how they implement this multiplication that we discussed, because it was the secret key interaction. So first we are deciding the region, vulnerable region. So even in implementation, the first interaction happens when we are multiplying C with the S1. That's why it was a target operation, and it is mostly being used when side channel attack in ML-DSA. But before this multiplication, they are going into this entity transform. It is a basically number theoretical transform. It is very similar to fast Fourier transform. It is basically for integer numbers. And so S1, it is a polynomial vector. So they are going one by one to entity transform, then being multiplied with C. But idea is that after converting entity, it means that we can multiply each coefficient with each coefficient. So it means that the first coefficient S1 will be multiplied with the first coefficient of C. The second one will be multiplied with second one. So it is kind of more efficient, because school book multiplication giving like n square complexity, but this one giving n log n. And I want to talk about how did they implement this entity-based modular point-wise multiplication. They use two memories that is getting this coefficient one by one, and they have 4 multiplication core. It means that they are executing 4 modular multiplication parallel. And they had this mux going nice way. So they have a mux whether they want to make sure that the first data is coming or the data is already being written. So inside of this course, I will go a little bit deeper because I want to show which part was vulnerable. So inside of this course, they have a pipeline reduction algorithm for efficient modular arithmetic. So it was taking 23-bit inputs and generating 23-bit output. And it was basically processing 46-bit intermediate products. And it wasn't like other reduction algorithms like Barrett or Montgomery. They were using a pipeline structure that is giving a constant time modular reduction. And the reason that they use is because of this unique feature of Q, in a way that they were able to design this unique reduction. So this is the reduction. So basically, I am zooming into this course. And when I was zooming in, this is what we have. So they are taking 23 coefficient from C and S1. And this multiplication is assigning to register. And this register wasn't protected. It means that there wasn't any masking, there wasn't any shuffling, which I will talk what are those. And after those, they were going over a multiple addition and also some shifting. And there was a other register being used. It was this arithmetic addition. And there was a second register that we can use. So, okay, we detect which register we are going to attack, but what is our methodology? We use correlation power analysis. It is an attack that allows to find the secret encryption key stored in the victim device, and it has 4 steps. So first, we are collecting power traces, gather many power traces while the victim device is running signing operation, and generate key guesses. So it means that we don't know S1, but we know the possible value of S1. It can be 0 all the way to modulo Q. And calculate this intermediate registers, which I show. This is the target register, and we are basically trying to calculate the value of this register based on the key guesses. And then after calculating this intermediate value, we are calculating their Hamming distance, or we can use also Hamming weight, but since it's the hardware system, we gotta use Hamming distance. The idea of Hamming distance is like how much the bits differ. So as you see, the first example, if I put Hamming distance function 1 0 1 1 0 with 1 0 1 1, we are basically XORing bitwise, and the result, how many bits we have, it is 3. But for second example, just only 1 bit change. So that's why Hamming distance is 1. And then we are correlating power consumption with Hamming distance. So this was our threat model. Send message, get signature. During this time, collect power traces, and put this correlation power formula to extract the secret key. So this was our setup. So we use picoscope to collect power traces during cryptographic operation. And also we use this FPGA boards, which we program with the open source implementation of ML-DSA. And we also use chip whisperer setup to provide to get the data as synchronization. And this is how we collect power traces. So during this encryption is going on, we got the whole ML-DSA. First, plot showing the whole signing operation. So I talk about the rejection loop, right? As you see, it has 4 rejection. After 4 times, they are finding the valid signature. And this is when I want to zoom into this point-wise multiplication, I can see how the coefficient being multiplied by analyzing the power consumption. And then I said I will generate key guesses, but how? So I know that it will go 0 all the way to 1, all the way to Q, and I will calculate this Hamming distance, which is measuring the number of bit transition. It goes 0 to 1 or 1 to 0. Because if it's stable, it is, let's say that is 0 and it stays 0. It means that I'm not giving that much power to change the switch signals. But it is 0 and it is converting to 1, it will require more power to make this change. And I generate all the key guesses. Then I multiply with the C, because this was the register that we are attacking, right? The multiplication result with C. Then I name this intermediate value V, and this V will give me the leakage analysis, which I will calculate the Hamming distance, the previous state of V and the current state of V, to understand how many bit change and how many power will correlate with this data. So a little bit confusing, that's why I want to show. Let's say that in the cycle 1, when we multiplied, we have formed like this EFI with the non-key. And it is this is the binary representation of EFI, EF. And after 1 cycle, we are saying that this register value change to 9A. And then I'm XORing this 2 value, and I have this value. Then I'm calculating how many bits do we have? 5. It means that 5 bit change. That's why if it's 1 bit change, it is going to require less power, but it is 5. So this is basically giving my idea how to correlate with power. And then after generating all the key guesses and their Hamming distance, and I'm basically calculating this Pearson correlation table, which for each power sample point, I'm computing the correlation between the Hamming distance and the actual power sample for the trace. Then the highest correlation giving me, this is the correct key. So power sample point, you can think about the plot that I showed. So it has the x-axis, it has like n power sample point, and I'm basically calculating the correlation for each sample point with the Hamming distance, and the highest correlation giving me, this is the correct key. And so this is how do we convert this table to plots. As you see, there is a peak in the first plot. So it means that at this point, there is a correlation between data and the power traces. And this is my correct key guess. And the second plot, it is another way to represent it. I'm basically calculating Pearson correlation over the number of traces. And it is a visible correct key guess correlation after 4,000. But I want to show when the correct key guess is extremely visible, which is after 10,000 number of traces. And this was the second correlation for the second register that I took. It was another register that we attack. So we don't need to specifically attack this register, but I just want to show which part that we need to protect. Even we only protect the first register, we have this other vulnerable register. And I want to discuss and compare our work with the previous works. So there were two papers about this ML-DSA attack. They basically attack the lithium implementation, but NIST renamed the lithium as ML-DSA and changed like a couple of things. But their study wasn't considering ML-DSA. They used like one of the lithium implementation, one of the researchers. So Stefan did profiling attack. Profiling attack is basically using AI. They are sending they are getting multiple traces with known keys. They are basically training a model. And then when their attack phase, they just want to get one trace and putting this model to find the secret key. But this is not that much real world application because they require almost 35 times traces compared to us. And there was another study that done by, I think, Chinese Academy of Science. And they also collect 70K power traces. And I just want to highlight that this implementation, their implementation wasn't deployed in real world application, but we target the real world application that is side channel vulnerable, and that can be done attack.
What has the type, the profiling or non-profiling?
Yeah, so profiling, it is basically AI based. So they are first training a model, but non-profiling, it means that doesn't require any profiling, doesn't require any prior template or any model. Ours is like that. We are assuming that the attacker doesn't have pre-collected traces, doesn't have any template. It just enters the room, collect power traces, then calculate the CPA. But their idea is that the attacker first by himself train a model collecting power traces. And by collecting these powers also, he knows the known key values and then train a model. Then enters the room, just collect one power traces, then put it in this model to extract the secret key, which is requiring more power traces because first you gotta train the model. And it is a hardware, it is not a software implementation. Hardware, it is extremely noisy because it is not doing only one job. There's many parallel execution, so it is extra noise that's coming from the other registers. But for software implementation, it is easy to manage this noise. And so I show my result, but I wasn't able to discuss how to mitigate these attacks. So this attack is a physical attack. That's why we need to talk about the physical countermeasure. There's a main technique The first one is called hiding. The other one is masking. So for hiding, we want to make sure that let's balance this power in a way that it is not going to give any idea to attacker that gives ability to understand the secret key. The most common one that being used in industry is shuffling. We are basically randomizing the execution order. So let's say that we said that we are putting this coefficient one by one, and they're basically shuffling this order in a way that even attacker have this correlation, he's not going to understand which secret key coefficient being used. And the other method is WDDL. So it is basically a hardware. It is called like complementary circuit. We are adding additional circuit to actual circuits that's vulnerable, and there's going to be additional power, and still the attacker is not going to be able to understand. And the other method is masking, which is introducing random values to break the correlation between side channel measurement and secret data. And this is the only countermeasure that can be formally verified, which there's a model called PNI, TSNI, and this model allows to verify formally, which is making a strong theoretical defense.
Wait. There is a mathematical proof that this is how much this is effective.
Yeah, they have like they are explaining this circuit as a graph, and they are saying that attacker has ability to access T probes. I'm not that much confident about their mathematical, but I have general idea about they are creating a model. They are explaining this circuit as a graph, and they're saying that attacker has ability to access this probe, this much like register. But even though he has access of this register, because of this additional masking, which is additional shares, it doesn't allow attacker to calculate these intermediate values, which I will talk about this randomization, how to create shares and etc. But it is general idea of how they are verifying, because they already predefined model, and they're basically putting their masking to this model, and they're showing that still it is secure. Because shuffling, it is okay, we are shuffling, but if we collect enough power traces and if we do like additional calculation, we can still understand. We can try all the combination of this order to find the correct key, which will require additional resources, but still there is a limitation of shuffling. So the idea is that let's say that we are randomizing over 2 bits, because we said that 4 core that's happening. So if we randomize this 4 cores, still there's a one possible that is giving the correct key guess. So that's why. But masking, this is how do we masking? So we said that we are attacking multiplication, and my suggestion is that let's protect this multiplication. So let's say that I want to multiply A with B, and I want to keep my result in finite field 2 power 4. It means that it is going to be eventually between 0 all the way to 15. And let's say that A is 2, B is 3, and the result going to be 6. But there is already gadget that is already implemented by, I don't remember the name, but I think it's being implemented 5 or 6 years ago, maybe more than that. So they are basically creating shares using random values. So I will keep this R1 0 for simplicity. I just want to explain how to create shares and how to get the same result. It can be any value. And R2, let's say that 8, and R3 is 1. So I will use R2 and R3 to split A and B. So A0, it means A minus R2, the number that I'm going to use to split A. And A1 will be R2 again, it is 8. And B0 is going to be again B minus the random value, and the B1 will be random value itself. Okay, now I have this A0, B0, and I will put this gadget. First, I'm calculating this A0, B0. it is 4. Then A0, B1, it is 10. Then as you see, my M0, since R1 is 0, M0 will be 14. Then I'm doing the bottom part. First, I will multiply A1 with B0, it is 0. Then I multiply with A1 with B1, it is 8. Then M1 becomes 8. Then I add that, it will 22. When I get the modulo 16, it is 6 again. So the result is same, but I just additional random value. I created these shares and I didn't get these shares together. I never multiply or add A1 with A0. This is the idea of masking, creating a shares and making sure that this share is not going to be together, not going to be merged. And this is the mathematical part, but they need additional register to mitigate this the wire delay. That's why they are putting this register before this addition and multiplication. And this gadget called first order mask architecture based on HPC1. And it is breaking the power consumption, a correlation between power consumption and secret data. And they did this first order secure masking scheme for FPGA. But there's a limitation still because it is requiring more gates and registers. And we are introducing additional randomness, which is also requiring resource. And it is increasing area and it's giving latency for this FPGA and ASIC implementation. So this is my conclusion. We show that ML-DSA, the hardware implementation of ML-DSA for this implementation is vulnerable to side channels. And we highlighted need for proactive countermeasures such as masking and shuffling. And we want to emphasize the importance of securing hardware cryptographic implementation against both mathematical and also physical attack. And our research should explore the area that we want to also expand our attack in a way that we can also do this profiling attack. And if you have any question, I would love to.
Yeah, thank you very much. Very nice talk, very informative.
Thank you so much. I thank you so much for me.
A low level for us, poor mathematicians. So this is this is just the target. This is the implementation by this
Companies.
company, right? What is it called?
Microsoft did this.
So it's Microsoft product. What was it called again?
They called is Adams Bridge. It was Calyptra. So
Okay.
Calyptra name of this root of trust, and they name ML-DSA as the Adams Bridge because it was like a bridge with the classical and the PQC algorithm. And I think they protected, by the way, but for our paper, it wasn't protected at that time. And then we published paper and they email us. We already protected. Why did you do that? But it was okay.
Okay, so they
Yeah.
they're already
They ordered that masking, they ordered that shuffling, but it was late. But
okay.
yeah.
What about other kind of physical attack? Do you do like a differential attack or EM other things like that, or even a fault injection?
Yeah, I think it is still vulnerable to fault injection because they didn't propose any shields to their ASIC design, but so I don't know how to use this fault injection thing. We have in lab, but I gotta learn. But EM emission same. It is, since it is masking, it is not going to be vulnerable to side channels. Still we gotta see because there is another cryptographic guy, I forgot his name, but he got this TVLA even for the protected version, and it shows that it was still leaking. So because I guess they didn't protect for the key generation parts, they just protect the signing parts. And for, as I said, the other side channel attack, DPA, CPA. So I didn't try DPA because DPA is kind of harder when it comes to hardware. Because DPA, we are basically creating two sets by analyzing, let's say that the register is 0, register is 1, and then analyzing this power. So this hardware, it has noise. As I said, it is because making like execution, parallel execution. So it is hard to distinguish this power consumption by looking at just one bit. But correlation is making in a way that you can understand there's a correlation when I collect more power traces. It is easy to follow this attack and see the results. Yeah, and also there's a simple power analysis. I didn't see for a long time how this CPA, because they did, I think, simple power analysis for square and multiply thing. There's a straightforward algorithm. They can see basically the bits and the power trace. But again, it is like ML-DSA whole big operation that is requiring thousands of registers, and you cannot see the power trace easily. Yeah, that's why.
Well, also another question, like I see that these rules of trust also they contain the modules for implementing like ECDSA and other things. So is it possible to kind of maybe with the fault injection to force one of these other things to be implemented, and then to have to basically leak the key by just redirect by just changing the
I know that how to attack very specific part, but I think it is maybe doable. But I'm not sure. Yeah, maybe there's online question, by the way. I didn't. Maybe.
anybody online has questions?
Okay.
Well, then join me to thanking Merve again. Thank you very much.
I think so much for having me.
You're 2 weeks.
Okay.